All right, everyone, we're going to talk about bifurcation theory today. So bifurcation theory is a fantastic topic in dynamical systems in which you start to think about the parameter dependence of the dynamics itself. So oftentimes in dynamical systems you have different constants and coefficients that are parameters, and those parameters can change the behavior of the system. And that's what bifurcation theory tries to address in some kind of formal way, come up with a way to start to characterize the different types of transitions and behavior of your system. In other words, bifurcation points in which the path of these trajectories or behaviors changes. So let's talk about the general formulation of this thing. We want to think about some dynamical system, dx dt equals f of x. And so it's some given dynamical system. The thing I want to point out here is that I'm going to explicitly give it some kind of parametric dependency on some parameter mu. So mu is in there on the right-hand side. And the idea here is that the behavior of the system, the parametric behavior of the system, is going to change with respect to mu. And so what I want to do is start to characterize, first of all, where do these transitions happen, and what happens in these transitions. The really amazing and remarkable thing about doing sort of these bifurcation studies is you start to see there are universal types of transitions that occur. And what we're going to consider is what those look like. So there's canonical forms under which the transition happens, and we want to understand and study them because almost everything we see in nature comes from, when we see changes in behavior, can be brought down to these canonical forms, or what are called normal forms or universal unfoldings of bifurcations. Okay? So it's not like every problem has a different way it changes behavior. Every problem essentially comes down to a specific form of how transition happens. So that's what we're going to cover in the next two lectures. So I want to give this, introduce this in context of a few of the dominant examples of what these bifurcations look like. So I'm going to give you the canonical forms. And we're going to study them, and you're going to see how these behaviors change as a function of mu. So here's the dynamical system I want to consider to start with. And what we're going to show is what's called a saddle node bifurcation. Okay? And so the parameter mu is there, and it's going to change the dynamics. So dx dt equals mu minus x squared. It's a nonlinear differential equation. And what I want to start to understand is its behavior, especially as a function of mu. So the first thing we're going to do with a system like this is we're going to look at the equilibrium solutions. Where is it that dx dt equals 0? Well, it's here, when mu minus x squared is equal to 0. Along those solution branches, notice that you can get a very specific relationship between x and mu here, which is just this. These equilibrium solutions are plus or minus square root of mu. In other words, along those curves, nothing is happening. The dynamics is not changing because dx dt is 0. Okay? So equilibrium solutions are really important. And when we started this set of lectures in this class, we talked about looking at equilibrium solutions and perturbing around them to understand the global dynamics. Well, now our equilibrium solutions are parametrized. So we don't just get a point, we get a whole line of solutions which depends explicitly on the parameter mu. Okay? So particular x is square root mu, x is minus square root mu. But what I do want to do is understand what happens under perturbation around these two solutions. Okay? So this is, again, where perturbation theory starts to play a role, right? We want to take the solution, perturb it a little bit, and see what happens. And in doing so, we get a full understanding of the dynamics itself. So here's what the perturbation does. Perturb around these solutions. X naught is either that square root mu or minus square root mu. Okay? And so we're going to perturb around that. With the x tilde is going to be small. I could formally write x naught plus epsilon x1 plus epsilon squared x2, just like we did in regular perturbation theory. But here what I'm going to do is just say x tilde is going to be small, and I want to just keep the order epsilon contributions of the small terms. Anything with x tilde squared I'm going to throw away. It's much smaller. So that's like removing the x2 terms. Okay? So we're going to just do this perturbation around here. And here's what you do. If you plug that into that governing equation for the saddle node equation, here's the dynamics around x naught. It's a linear differential equation. dx dt is equal to minus 2x naught x tilde. And the solutions just look like this. Trivial to solve. Linear differential equation, first order. So there's the solution. It's an exponential solution. This is what you always try when you have a linear differential equation with constant coefficients. You put in an exponent. There's the solution. So we have the solution to this. And I want to point out to you, you have e to the minus 2 x naught t. So if x naught is positive, then this goes to 0 as t gets big. So those would be stable solutions. If x naught is negative, then these solutions, that's going to be a negative there with that negative here. That's going to be a positive exponent. So as t gets big, this is going to blow up. Okay, so that's what we're looking at then, is we have this behavior which is either it's going to go to 0 or blow up depending upon if x naught's positive or negative. But remember, x naught, I had two solution branches. One, which was square root mu. The other, which is minus square root mu. So one of them was positive, and one of them was negative. So I have a stable branch and an unstable branch of solutions. So let's just plot this and what it looks like. And here's the picture I want you to keep in your mind. So the solutions to this are this branch here, right here. Starts here. This is the square root mu branch. The second branch starts here, minus square root mu. Okay, so I have two branches of solutions. Here I've just drawn the 0 line. Okay, that's where just as an axis point. And so I have that top branch of solutions and the bottom branch of solutions. And I just said that if x naught's positive, in other words, on the branch here that x naught is square root mu, things are stable. In other words, around here, all the solutions get pulled into it. In other words, all the solutions near there get popped onto that solution branch. But when x naught's negative, all the solutions on this branch exponentially move away from it. So what this shows you is the flow field of the dynamics around those two branches. So here, right, so all the solutions come up to this branch because it's stable. Solutions from above come down to this branch depending upon where you're starting. Here, everything goes away from this branch. So this is an unstable branch. That's a stable branch. If you're over here, okay, there's no solution out here. So the solution, there's no equilibrium solution out here. All the solutions just go this way. So the solutions just go towards negative infinity. So this gives you an idea of what the structure is. There's a transition instability that happens right here at the bifurcation point where you have a stable solution up here, an unstable solution down here. So that's the idea of bifurcation theory, is to capture those behaviors where you have transitions, instability. And the stability here is the upper branch stable, lower branch unstable. The bifurcation theory, we just worked it out, tells you how that happens, and this is called a saddle node. It is a canonical structure that shows up all over the place. It's a universal unfolding of a bifurcation. And in fact, I'll show you an example in the next lecture of how you take a more complicated system, and near these bifurcation points, if you do an asymptotic approximation, you find that you get these leading order different types of bifurcation structures, whether it's saddle node or some of the others we will talk about now. So let's take that problem, modify it slightly. So now I have dx dt is mu x minus x squared. Before I didn't have that x there, I just had mu minus x squared. And this was called a transcritical bifurcation. I'm going to show you the behavior of this thing. So again, the dynamics depends upon mu. And so what we want to do is start to investigate this problem and understand what happens as a function of mu. Same process as before. We look for equilibrium solutions. So what we do is say dx dt equals to 0, and that means that mu of x minus x squared, or if I could pull out a common factor of x, I get x times mu minus x is equal to 0. There's two solution branches. X naught is equal to 0, or x naught equals to mu. Okay? So I have these two solution branches, and for each of these solution branches, what I'd like to do is to do a perturbation analysis around these branches. So here it is. X is equal to the equilibrium solution plus a little bit of perturbation to it. So the equilibrium solution here, remember, was x naught is either equal to 0 or is equal to mu. So I'm going to go ahead and do the perturbation expansion around this. And here's what you find. When you plug that back into the to the full problem, you find that when you, the corrections, the dynamics for the x tilde is given by this linear equation here, linear differential equation, mu x minus 2 x naught x tilde, a linear constant coefficient. You can write down the solutions. There it is. And notice you have this e mu minus 2x naught. So the sign of this mu minus 2x naught matters a great deal. Is it positive or negative? If it's negative, the solutions go to 0. If it's positive, the solutions blow up. So imagine the solution where x naught is equal to 0, for instance. That's one of the equilibrium solutions. Then this 2x naught there, that 2x naught just drops out, and you have e to the mu t. So if mu is positive, it grows, and if mu is negative, it decays. Mu is negative is stable, mu is positive is unstable. You also have the solution x naught is equal to mu, so you get mu minus 2 mu, so this will become minus mu. And then it's the opposite. If you have minus mu t there, if mu is positive, it's stable. If mu is negative, it's unstable. In fact, we can show this in this summary graphic. There are two solutions to this problem, equilibrium solutions. This line here is mu equals 0. This line here is x is equal to mu. Okay? Sorry. So this line here is x naught is equal to 0. This is x naught is equal to mu. Sorry. Okay? So I have two solution branches. There they are. And they switch stability both as mu changes from positive to negative. In particular, this x naught equals 0 branch is actually stable all the way to here. When mu becomes positive, it becomes unstable. So everything gets sucked onto this solution branch up to this point here, and at this point everything moves away from it. It's a linearly unstable. Whereas this branch here, this line here, x equals to mu, over here the solution branch is unstable, so everything moves away from it. But as soon as you get to this here, everything pops onto this. So you see there's a transition in stability. So if mu is negative, you're on this branch of solutions. And as mu increases, at this point here, a bifurcation occurs. That 0 solution becomes unstable, and you jump to this other solution branch, which is x naught is equal to mu. So when you do it in this form here, this is what's called a transcritical bifurcation. You jump from one linear branch to another linear branch. You just get the transition in stability right at mu equals 0, and you get the transition. Okay? And you jump branches. So that's called a transcritical bifurcation, or a transcritical node. Another canonical form that shows up across physics and engineering. Let's do a third example. It looks very similar to the transcritical, but now instead of mu x minus x squared, now we have mu x minus x cubed. This is what's going to be called a pitchfork bifurcation. And again, the dynamics of this system will change as a function of mu, this parameter here. Same process as before. Look for equilibrium solutions. Here they are, mu of x minus x cubed. Plug this in here, you get this, and you set it to 0. And in fact, there's 3 solution branches, and here's what they are. X equals to 0, x is equal to plus or minus square root mu. So now you have 3 solution branches, and for each of these solution branches, you have to determine, are they stable or unstable? For what values of mu are they stable or unstable? So same kind of thing. Perturb, x is equal to x naught, which is one of the equilibrium solutions, plus x tilde. Here's your generic representation of the linear stability around the x naught. It's given by here. So all you have to do is plug in your specific x naught you're looking at, because here's your solution. So you plug in your specific x naught, and notice what you have here. You have some exponent, and you really care about, is this parameter here, mu minus 3x naught squared, positive or negative? If it's positive, this is unstable. If it's negative, it's stable. So you can do that for each of the 3 branches. This is a very simple calculation to do. And when you do that, here's what you find. This is the Pitchfork bifurcation. So you have a solution branch here, which is x naught is 0. You have the solution branch, x naught is plus square root mu, x naught equals minus square root mu. So these are the three branches. They live only, the three branches only exist for mu is positive. For mu is negative, only the x equals 0 solution exists. And in fact, what you can find is the x equals 0 solution is stable for mu being negative. So all the solutions for mu negative collapse down here to 0. But as soon as you hit mu equals 0, that changes. The 0 solution becomes unstable. But the two branches, the square root mu and minus square root mu, are both stable. You can just go plug that into you can find that the exponent is negative on these two branches. So they're both stable. So notice what happens. All the dynamics collapses to 0 here. And once you get past 0, you either jump up to this branch or down to this branch, depending upon which side of x equals 0 you're on. So if you're above x equals 0, you always jump to this branch, or you come down to it from above, or from below you come up to this branch, or if you're below x equals 0, you jump onto that branch. So you get these three branches over here. Two of them are stable, and these two stable branches are separated by an unstable branch. You can't have two stable branches next to each other. You always have to have two stable branches separated by an unstable branch. And that's exactly what this shows you. That is called a pitchfork. And it's a pitchfork because it looks like a fork. Right? You come here, depending on what side you're on, you either go up or down to one of those stable branches. The final one I want to illustrate to you, in fact, the four that I'm illustrating to you are kind of the canonical examples that often show up in many examples, which are, and we're going to talk about this in the next lecture, what's called normal forms. These are the normal form bifurcations that happen in many physical engineering systems, right? You can always do asymptotics and show these are the canonical forms that you get for the bifurcations that occur. And here we're going to consider what's called a Hopf bifurcation. And the Hopf doesn't have necessarily a generic form, but what I want to show you is a form that you can see almost everything we need to illustrate for the Hopf. So now I'm taking a system. It's a 2 by 2 system, dx dt, dy dt, and of course it's nonlinear. I have an x squared minus y squared here, x squared minus y squared there, times x and y. And so this is just a system, and in fact this system is going to produce what are called limit cycle oscillations. So let me go ahead and start to look at this more carefully. First thing as before, just like we did everything else, we look for the equilibrium solutions, and there they are. Set dx dt equals 0, dy dt equals 0, and this is what you get. Okay? Now once I've done that, I'm going to now perturb around the equilibrium solutions to this. And so first I want to do the equilibrium solution at the origin, because that's the one that actually exists. So I perturb around the origin. There it is. Perturb around the origin, do a linear stability analysis. Here's what you get. And I can write it in this form here as a system of 2 by 2 differential equations. And then I can look at the eigenvalues and eigenvectors of that equation there. So this is like a phase plane analysis. And around the origin, this is your behavior. And as mu goes from being negative to positive, you're going to find there's a transition in the stability of the 0 solution, which is the only equilibrium solution of this system. So generically, your eigenvalues are given by this. You're going to get some real part plus some imaginary part, and so we can normalize it so that the oscillation frequency is 1. So you can actually, this is exactly the eigenvalues of this system here. So if you compute those eigenvalues, here's where they are. And notice I have mu is the real part plus or minus I. So this is telling me that I'm oscillating. There's an imaginary part and with frequency 1. And the mu is the real part. If mu is positive, then I have an exponential growth. If mu is negative, I have exponential decay. So the stability is completely determined by mu, which is, if it's negative, the origin is, the 0, 0 solution is stable. If it's positive, it's unstable. A simpler way to represent this is to say that r squared is equal to x squared plus y squared. In fact, this is a very nice form. This specific set of differential equations actually, if you write it in that form in terms of radial coordinates, it has this very nice representation. And what I want to show you here is if you look at this thing here, look, you have you look for equilibrium solutions, and then you have these branches of solutions in these radial coordinates, which is r is equal to mu, right? Square root mu, sorry, and r is equal to 0. And then you can do a stability around those. And so here are your solutions to that. And I just wanted to point this out, that you can actually go ahead and rewrite this in terms of polar coordinates to work this out. This specific example, you can't always write this in polar coordinates, but this one, the specific form I gave you, came out to be a very nice form in polar coordinates. There it is. And you can write down the solution, actually. And so here's the picture. This is the main thing I want you to walk away with. What we just showed with this example is when mu, and now I do it in 3 dimensions. So in this, so we look along this direction here, this axis, this is mu, that's the parameter I'm varying. And then the plane that's sort of orthogonal to this, right here, this cut across here is the xy plane. Remember, it's an x dot y dot system. And so when I look in the xy dot plane, and now I look at what happens as a function of mu, if mu is negative, this thing was stable and oscillatory. So if I start with some generic point, notice what's going to happen. It's going to basically be spiraling in to the solution at u equals 0. So it's stable. And the way it's stable is it sucks solutions in that spiral into it with a given frequency. And that's exactly what this trajectory is trying to represent for you. And that's generic for everything that happens for mu equals negative. Now once you cross this line here, at this point here, this is where the bifurcation point is. At that point, now you have in this, if you look at the cylindrical coordinates or polar coordinates, you have another branch of solution that pops up. And along that branch of solutions, first of all, the mu equals 0 solution goes unstable. And now you oscillate and exponentially grow away from the origin. So now you kind of circle out, and you end up on this branch of solutions that go like r equals mu. So now you're just oscillating on here. So notice it's not like a generic equilibrium solution where dx dt is 0 and dy dt is 0. Here, dr dt is 0 on that branch of solutions if you write it in polar coordinates, but you're simply cycling around that branch. So Hopf bifurcations are fundamental. It's an instability that when it occurs, an oscillation is observed at the bifurcation point. And this is exactly what this is trying to illustrate for you. The solution, if mu is negative, it's going along, it's stable, and then when you cross and go into mu is positive, it's unstable, but what you see is unstable with oscillations. In other words, 2 eigenvalues cross from the left half plane to the right half plane of instability at characteristic frequencies. And those frequencies are exactly what's observed here. Those are the imaginary parts in that bifurcation. And this is something that happens and is canonical across physics and engineering systems. So the Hopf is an oscillatory instability. That's another way of saying that. So what I just showed you is 4 canonical examples of bifurcations. And we're going to build on this. And the most important thing to recognize is that when you have a dynamical system and you have some parameters in there, the behavior can fundamentally change as a function of those parameters. What we just showed here is by doing perturbation theory around the transition points, you can characterize the kind of transition that will happen there, right? You can characterize the bifurcation that will occur at these transition points and these parametric dependencies. And so bifurcation theories is all about trying to give you a theoretical construct to understand those transitions and to write down exactly what forms they are and in terms of what canonical shape they take at that transition point. Okay, more on this in the next lecture.